we'll now look at Euclid's algorithm. So let A be equal to BQ plus R, where A, B, Q, and R are integers. Then the GCD of AB is equal to the GCD of B and R. So basically, if I'm looking at the GCD of two numbers, I can divide those and replace the larger number with the remainder. So for example, let's find the GCD of 287 and 91. So I'm going to divide 287 divided by 91, which, this should be a 91, is 3, with a remainder of 14. So the GCD of 287 and 91 is the same thing as the GCD of 91 and 14. So these numbers are going to be easier to work with, and we can even simplify it further. 91 divided by 14 is 6, with a remainder of 7, so I can replace the larger of the two numbers with a 7. So this is also the GCD of 14 and 7, which is even easier to find. If we tried to divide these, we get 0, a remainder of 0. So whenever we do this method, our actual GCD is the last non-zero remainder, which is 7. Let's find the GCD of 414 and 662. Dividing them gives a quotient of 1 and a remainder of 248. So now we do 414 divided by 248. This gives us 1 with a remainder of 166. So 248 divided by 166 is 1 with a remainder of 82. 166 divided by 82 is 2 with a remainder of 2. Now I have 82 divided by 2, which is 41. So my actual GCD is the last non-zero remainder, which is 2. So Beswat's theorem, if A and B are positive integers, then there are integers s and t such that the GCD of AB is SA plus TB. So I can write the GCD as a linear combination of A and B. For example, let's consider the GCD of 252 and 198, which is 18. And we want to write this as a linear combination of 252 and 198. So I start by dividing. 252 divided by 198 is 1, with a remainder of 54. I then can do 198 divided by 54, which is 3, with a remainder of 36. I then have 54 divided by 36, which is 1, with a remainder of 18. And then 36 divided by 18 is 2. So far I have confirmed that the GCD actually is 18 using Euclid's algorithm. And I'm now going to use this data that I have to find this linear combination. So I'm going to start. I get to ignore this last case, and I only have to consider these three. So I'm going to start at the bottom and subtract the 1 times 36. So I have that 18 is 54 minus 1 times 36. My second equation, I'm going to subtract that multiplication to solve for 36. I get 36 is equal to 198 minus 3 times 54. And then finally, the top equation, 54 is equal to 252 minus 1 times 198. So these are the same equations. I just solved them for the remainder. So I'm going to start with this one that's currently on top. And then I'm going to realize that this has a 36, which is given in the second equation. So I'm going to change that 36 using this second equation. This is 54 minus 1 times 198 minus 3 times 54. Multiplying that out gives me 54 minus 1 times 198 plus 3 times 54. I then see that I have a 54 here and here. So 1 plus 3 is 4. So 4 times 54 minus 1 times 198. I now have this 54, which corresponds to this last equation. So I'll do this process again. So this changes to 4 times 292 minus 1 times 198 minus 1 times 198. Multiplying is 4 times 252 minus 4 times 198 minus 198. I have the two 198s, so negative 4 minus 1 is negative 5, and that should be a 2. Small typo there. So now I have 4 times 252 minus 5 times 198. So now this is in the form SA plus TB. So S is 4 and T is negative 5. We'll do one more. So we'll start by finding the GCD. 2347 divided by 123 is 19 with a remainder of 10. 123 divided by 10 is 12 with a remainder of 3. 10 divided by 3 is 3 with a remainder of 1. And then 3 divided by 1 is 3. So my GCD in this case is 1. And I can ignore this last equation. So just like with the previous problem, I'll start by solving each of these for the remainder. So this last one, 1 is equal to 10 minus 3 times 3. The second one, 3, is 123 minus 12 times 10. And then the top equation is 10 equal to 2347 minus 19 times 123. So I start with this top equation here, and then I realize that this 3 can correspond to this second equation. So this is 10 minus 3 times 123 minus 12 times 10. Multiplying that out gives me 10 minus 3 times 123, and then negative 3 times negative 12 gives me positive 36 times 10. I then have a 10 here, and a 10 here, and this is 1 plus 36 gives me 37. I can now see that this 10 can correspond to this last equation. So this is 1 is equal to 37 times 2347 minus 19 times 123 minus 3 times 123. Multiplying this out, 37 times 2347, and then 37 times negative 19 is negative 703 times 123 minus 3 times 123. So I have two 123s, so negative 703 minus 3 is negative 706. So once again, here's S, and here's T.